So we looked at some of different types of heat exchangers, and now we are just like going to talk about how actually we classify different heat exchangers. So for example, heat exchangers can be direct or indirect. So when we are talking about direct heat exchangers, it means that we are adding the hot fluid, we are mixing the hot and cold fluid and then increasing the temperature of the cold fluid. While when we are talking about indirect heat exchange, it means that we are exchanging heat through a surface, like we discussed, for example, different heat exchangers. Okay. Then we talk about the compactness of the heat exchanger. So the compactness of heat exchanger can be used, for example, to define the size of heat exchanger in terms of its surface area to volume ratio. So if an exchanger has a high compactness, it means that its volume is quite small. Okay. And if it is non-compact, it means that it's going to take a lot of space in industry as well. Okay. So depending on the type of industry and application of industry, you have to take into account what is the compactness of the heat exchanger. In terms of compactness, what it means that how small the pipes and diameters are. So for example, shell and tube is not very compact, while for example the finned heat exchangers are quite compact. And this is just to give you an example that human lungs are super compact because they have very fine surfaces. Okay, so this is just for information, not related to heat transfer. Another type of heat exchanger classification can be based on construction type, and that's what we discussed in the first few slides. It can be a double pipe where the heat exchanger is between two pipes. It can be plate type, or it can be shell and tube, depending on different types of construction. Okay, so these are just some names. You are not supposed to remember these names. I just introduced the most common ones: the plate type, shell and tube type, and finned heat exchangers. Okay. Then we can have classification of heat exchangers based on their flow arrangement. So we can have parallel flow heat exchangers, or co-current heat exchanger, counter-current heat exchangers, cross-flow heat exchangers, and multi-pass heat exchangers. Okay. So just to show you what these are. So here we have, for example, for the case of shell and tube heat exchanger. So parallel flow heat exchangers are when the two fluids, for example, the let's say in the shell we have hot fluid. So the hot fluid and the cold fluid are moving in the same direction. That is what we call parallel flow. And if they are moving in the opposite direction, we call them counterflow. And if they are moving at 90-degree angle, so as you can see here, so we call them cross-flow heat exchangers. And then we can have a situation where we have multiple pass. So for example, shell and tube heat exchanger, in the same shell, we can either have multiple tube passes, or we can have one tube pass and multiple shells. Okay, and we will see that in much more detail in the next lectures. So we can also classify heat exchangers based on their heat transfer mechanism. So for example, if there is a phase change involved in the heat exchanger, like steam, if steam is condensing in the system, forced or free convection if you are using, for example, air, or you are using fan, or it is just by natural, for example, wind. So it can be classified based on that. If it is a phase change, then we call it boiling or condensation, like in boilers or in condensers. And finally, we can also have a kind of a combination of different mechanisms of heat transfer, like in furnaces, where we have radiation convection together. So if we look at shell and tube heat exchanger, that is one of the most common heat exchangers, and that for sure you will see in industry if you for example, in your professional life. So we are going to talk about now shell and tube heat exchangers here. So here, for example, we are looking at one shell pass and one tube pass. Okay, so here, for example, the hot fluid is entering from the shell side. Okay, and it goes around the tubes or in between the tubes and then goes out. And then we have the other fluid, the cooling fluid, let's say, and it's going through the tubes, and then it passes inside the tube where it heat exchange with the hot fluid, and then it goes out on the tube end. Okay, and here you see a similar thing, but in much more detail here. So here you have baffles as well, and these baffles are used in in the, for example, shell side to create turbulence. Okay, so by creating turbulence, again, you can increase the heat transfer. And this is how they actually look like in industry. So you can see that they are quite huge in size. So like, for example, this is almost 2-story tall. Okay, so this is a huge heat exchanger, shell and tube heat exchanger. And this is how it works, for example. So you have, this is the shell, and then you have the inlet of the shell and the outlet of the shell. And so this is a holder for the tubes where you actually place the tubes and then you fill them up. So you have a bundle of tubes. So depending on the surface area of the heat exchanger, you can calculate how many tubes you need, and that's what we will be doing in the next lecture. And then you have the spacer that actually hold everything together, and then through the spacer you introduce baffles, and these baffles, as I said, they introduce turbulence in the shell, and by increasing the turbulence you increase the heat transfer. And finally you place everything inside the shell, and then you put a header for the tubes. It means that the liquid that is coming out of the tubes will go in from this side and then exchange heat here and then go out from the other header. Okay, so this is how the heat exchanger, shell and tube heat exchanger look like. So in terms of the design of heat exchanger, we are primarily looking at two things. So one is that, let's say you have already an exchanger and now you have changed the temperatures or condition of the process, and you want to see that if the old heat exchanger would be good enough for the new conditions. Okay, in that case, what we do is that we calculate the heat transfer duty of this old heat exchanger to see that if it will fit for the new conditions, and that's what we call the rating problem. And the second kind of problem is that when you know how much heat duty you need, but you don't know how big heat exchanger you need, or what is the surface area of the heat exchanger you need. And in that case, we calculate what is the area required for a specific amount of heat transfer. Okay, and that problem is called the sizing problem. This means that we are sizing the heat exchanger. So both of these type of problems are very common in industry, depending on if you already have an exchanger or if you're designing an exchanger. So when we are talking about heat exchanger, we always look at this equation that accounts for the heat transfer through a surface, and in that here we have the Q, that is the rate of heat transfer, is equal to U, that is the overall heat transfer coefficient. And in simple sense, it means that how effective is the heat transfer. A, that is the surface area of the heat transfer, and that's what we are calculating when we are sizing the heat exchanger. Delta T is what we normally, for example, are given in terms of condition, and this provides us with the driving force of the heat transfer. Okay, so that is all for this part. Thank you for your time.